Our next speaker is Dr. Nathalie Garcon. I think it's fair to say that she is Miss Adjuvants. That is, she has achieved considerable scientific fame for her construction of important adjuvant systems. She is a pharmacist and a immunotoxicologist by training. That is, she has 2 PhDs, and she did postdoctoral research at the Royal Free in London, at Baylor in Houston, Texas, and then joined GlaxoSmithKline, where she successfully put together a number of important adjuvant systems, rose to be vice president, and she has more than 100 patents. So, Nathalie, the floor is yours.
Thank you for the introduction. Oh, I'm too short. I don't see the people anymore. But I'll talk without seeing you. I used to say that summarizing 20 years of adjuvant in 20 minutes, it's a challenge. I think now we are probably at more than 30 years, so I try to do my best. I think it's interesting to start by looking at what are the different type of vaccines, from the pathogen to live attenuated live virus vector, and then reducing the number of constituents from the virus going to subunit purified and purified with adjuvant. But I think what's important to know is that all vaccines are adjuvanted, whether it's endogenously through the pathogen or by what you add to the vaccine. Every single vaccine is adjuvanted. So adjuvants is not exactly a new science. It's the way we are looking at it now, which is. So if we look at the current vaccine challenge for vaccine, you have the challenges that are pathogen related, the ability to have an immune evasion and intracellular infection, multiple sero or genotype, antigen drift, moderate to limited efficacy of current vaccine, short duration of protection, complex life cycle, and latent disease. So there's quite a few challenges, but you need to put that in perspective with the challenge of the population that you want to vaccinate. So you have the elderly with an immunosenescence, you have chronic disease that induce a reduced response, infants with their immature immune system, and immunosuppressed or immunocompromised, including pregnant women. That is another difficulty. And on top of that, immunocompromised, you cannot use a live vaccine as a vaccine, it's a contraindication. So that add increased complexity. So for the population, what you want is to induce first the immune response. You want to increase the immune response. In certain cases, you want to broaden it, so go beyond the antigen and the genotype or the serotype, and ideally you want to induce an immune response that would last forever, ideally with one shot, and that you give at birth. So there's still some way to go. And when you look at those two things, you can mix whatever you want with whatever you want on the other side. It depends really on the population you're looking at and the pathogen you are targeting. So as far as novel approaches to vaccine, there's quite a few. There's DNA, mRNA, which is getting a lot of interest, and for which there probably will be a vaccine issued from that. The winner will be the one that is capable of formulating it. So there's still work for that. Live vectors, there's quite a few live vectors, and again, live vectors are certainly, they have their advantages, and there will be vaccine that will be based on live vectors, there's no doubt about that. Reverse vaccinology has allowed to analyze and define new antigen for vaccine in a much faster way than it used to be, and that's certainly implemented today. Self-amplifying RNA is another type of vaccine and antigen base, which seems to be fairly promising. But again, for this one, the formulation will be key. And finally, you have the adjuvant and the adjuvant combination that has been tested for more than 30 years now. And I will focus on that. So what is an adjuvant? It comes from the Latin, like this one, so it means to help. And it's defined as a substance which is included in a vaccine to enhance and modulate the quality and or strength of the immune response induced by the antigen. An adjuvant is not supposed to induce a new immune response de novo. And the disclaimer also is, if you do not need an adjuvant, don't use it. It's simple and basic, but this is very important. And adjuvant have really gone from a serendipity approach to their development to one which is much more rationally designed. And there's good things about serendipity too. I think that's the way we found the first vaccine. So there are, despite what is thought, there's quite a few vaccines with adjuvant that are licensed in Europe or in US or worldwide. And so the first one, and still the most used one, is aluminum salt. There has been more than 3 billion doses of vaccine that have been used around the world since aluminum is being used. You have various types of emulsion, MF59, ASO3, AFO3, ISA51. All those are based on emulsion. And then you have adjuvant that are based on the use of toll-like receptor agonist. ASO4 is with MPL and alum. ISA5, sorry, this is an emulsion. CPG is also, it's a TLR9 agonist, and ASO1 is a combination of a TLR4 agonist, MPL, and saponin purified form of, which is called QS21. So there are very different types of adjuvants. One emulsion is not the other, despite the fact that they can be the same type of physicochemical, they do not always act the same way. So if we look at hepatitis B, which is the first cancer vaccine, somehow, which we tend to forget, and that's a vaccine for that does immune evasion. There's not, I don't know whether it does that. There's not multiple serum genotype, and the vaccine today is certainly efficacious. So there has been a bug with my slide. So forget the left side. This is a vaccine that is given at birth most of the time for immunosuppressed people as well, and it is a chronic disease that you can have. So if we look at the impact of the adjuvant on hepatitis B, so it can be S or pre-SS antigen, but the point here is that there has been a study that looked at 4 different adjuvants, same study, so we can compare. One study that looked at CpG 1080, actually several, this is a Dynavax vaccine, which is licensed today, and another one with a different TLR4 agonist, which is a synthetic, which is called RC529. It's considered you are protected at antibody level of 10, so if you look, every single one of them is protecting, and some of them more than others, and you can argue that having 10,000 international units, you're more than protected. But clearly, depending on the adjuvant that you use, you can have different level of protection for the hepatitis B in particular. So one adjuvant is not the next. If you look at the human papillomavirus, so there's 3 actually, vaccines that exist today. Gardasil, which is based on aluminum, which has 4 genotypes, Gardasil 9, that has 9 serotypes, same aluminum, and Cervarix that has 2 genotypes, which are 16 and 18, so specifically for protection against cervical cancer, with aluminum. And what you see actually is that for 16 and 18, both vaccine, Gardasil and Cervarix, have about the same level of protection. But if you go down to what is highlighted in green and you look at the cause, SIN2 or SIN3, so it's the stage right prior to cervical cancer, you can see that actually, if you look at Gardasil and Cervarix, one with 4 genotype, one with 2, the level of protection against SIN2 and SIN3 is fairly different. The vaccine with the adjuvant ASO4 works much better. And the vaccine that now has 9 genotype reach a level of protection against SIN2, which is comparable to what you have with the adjuvanted vaccine. So on one side you have two genotype, one adjuvant. On the other side you have 9 genotype and another adjuvant. So clearly it's not the same, and you have the ability with an adjuvant to extend the protection above and beyond the genotype which is present in the vaccine. We talked earlier about influenza, so it's for elderly, for young people, it's for immunosuppressed individual, people with chronic disease. This is a pathogen that can have multiple genotypes. There's a drift. The efficacy of the current vaccine is limited, or at least it's questioned today. And frankly, in the case of influenza, it's very complicated to know what is going to be what, and it's probably a sign that the vaccine doesn't work well. There are several adjuvanted vaccines that are licensed with MF59, ASO3, AFO3, polyoxydonium, delta inulin. There's quite a few. Whether it's a split virus or a purified split virus or a recombinant hemagglutinin, different route of administration and for different population. This is a clear example of if you want to develop a more efficacious vaccine, you really have to choose your target population and your vaccine, because trying to do everything at once so far hasn't worked. Herpes zoster, so it's a therapeutic vaccine again. It's a vaccine which is designed for elderly, so with immunosenescence. So the existing vaccine has, I think, a moderate and limited efficacy, and actually if we look at what has been published, one is based on the attenuated virus, so you would expect that using the attenuated virus should allow to generate a protection. And what you see actually is that when you look at the overall protection, it's 51%, and from 60 to 80 years or more of age or more, you go from 64 to 18% protection, which is not good when you reach those age, and there's clearly an impact of the age. If you look at the alternative vaccine, which is a recombinant antigen, GE, which is combined with an adjuvant, and so it's, you would think one antigen, one adjuvant, it should not do better than a live attenuated virus. Actually, what you see is that from 50 to 70 years old, you have between 96 and 97% protection. And if you go from 70 to 80%, you're still above 90% protection. So you have the ability clearly with an adjuvant and a recombinant antigen to induce protection, which I would consider as a therapeutic vaccine. This is you are infected and you are chronically infected, which works better than a live attenuated virus at a dose, by the way, which is much superior to what you have in the pediatric vaccine. So the adjuvant makes a difference as well. What are the potential improvements? Today, what is being looked at for improvement of adjuvant is really more of the same. It's making the adjuvant more stable, biodegradable, having detoxified form, thermostable, variation on the same theme. Mucosal adjuvant, today there's not really a mucosal adjuvant that has shown promises in human. And cytokine, which have been looked at, but for which have pharmacodynamic issue, and today they have to be used, will probably be co-expressed in a DNA vaccine. So there's not really new ways or new completely transformational adjuvant that are coming. And today it's really focused on the principle of agonist, immunomodulator agonist of TLR or other pathways. So moving forward, I think we've heard that many times this morning, and it's the same for adjuvant. For the longest time, vaccines have been focused on the pathogen. We have a shift which is to the host, which makes sense because at the end it is the interaction between the host and the pathogen. And if you look at what's coming for vaccine, mass vaccination has always been what has been done. I think mass vaccination is not over for new vaccines, but there will be less and less vaccine that will be mass vaccination, except for pandemic situation. We are moving towards a population vaccination, adult, elderly, infant, pregnant women. We will most likely move towards personalized vaccination, and we can discuss what it is, but that's something that will come. And in between, we will need marker for safety, marker for efficacy. The microbiome will probably be key, and if you want to look at those markers, you will need to have companion diagnostic. And fast-acting vaccine is certainly something which is being discussed and looked at, and it can be by, and we heard that this morning too, giving the adjuvant before giving the vaccine, or having a process which is completely different and allows you to have people having an immune response much faster than what we see today, without adverse event. So in order to do all of that, we are moving to system vaccinology, and again, I will repeat what has been said this morning, where you have to take into account the host factor, which their immunological age, whether it's chronological or real. And we hear often that you start to age immunologically at 30 years old, which is depressing. But there has been a study made which shows that you have young, old, old, young. It's not that simple as far as your immune system. Your immune status, naive versus prime, which is key, especially when vaccine and adjuvant are being tested preclinically. It's not the same. Surrogate versus correlate of protection, and the status of an individual versus population, and essentially the host genetic the microbiome and the metabolism. I mean, as far as we are all different, and wanting to look at biomarkers that will reduce the population to low number of biomarkers may be difficult, or what you will have is what we know already and may not be of value for the development of vaccine. And the pathogen characteristic, whether it's stable or variants, the mechanism of control, the nature of the infection, the persistence, and the colonization and the immune training that can induce. And when you put all of that in face of the biological question you have for vaccine, can we have marker of susceptibility, infection, adverse event, and efficacy? Although when you look at clinical trials, and usually the more efficacious the vaccine, the more reactogenicity you have, which is a ballpark. When you look at the individual level, it's not true. You do have individuals that have a very good immune response and not that much reactogenicity and the reverse, so that has to be taken into consideration. And in face of that, you have all the enabling technology that will allow us to study that, and that are already being used and in place, which go from immunology, any omics we can think about, relevant animal model, single cell analysis, and last but not least, everything that has to do with data integration and analysis, and that goes through software development, deep learning, and artificial intelligence. Without that, we can generate as many data as we want. We won't be able to move. And the microbiota. And we need to move to system vaccinology to understand the mode of action of adjuvant. You need to understand how they work and differently in different people if you want to be able to improve them. And that has been published for the AS01, which is the adjuvant in zoster, the Shingrix, so the zoster vaccine. And clearly, it has been established what each of them do. However, it may not be that known, and this is really something that needs to be better understood, and actually, for me, reverse into the research part, that it is from those data that you will be able to improve on what exists today and have new vaccine with adjuvant that are more specific to your target. And finally, I think we need to do all of that so that we can have a population-targeted vaccination where ideally, and I'm sorry, I have put women, but I don't have the pregnant women, I'm sorry. And where those targeted vaccination, you can do it with, that allow you to define the population that you will vaccinate in, and also triage when you want to vaccinate. And ideally, what you want is a vaccine that is not reactogenic and beneficial versus a vaccine which is reactogenic but not beneficial. And we already see that that's possible. We are doing a study where we compare data in mice, rabbit for toxicology evaluation, monkey and human, and across all those species we look at the omic that are generated to see if indeed you have prediction that can be used for vaccination. Thank you.
Thank you, Nathalie. So, wouldn't you agree that the adjuvants are essentially stimulating innate immune responses?
Yes.
Isn't that the common? So,
well, not all of them, but
can you correlate the efficacy of an adjuvant with, let's say, responses stimulating CD4 T cells or CD8, or is this still empirical?
So, to my knowledge in human, there's no adjuvant that induce CD8 de novo.
Mm-hmm.
I don't know if anybody knows one, but I haven't seen any. As far as, yes, an adjuvant that can have an impact on CD4 T cells, and the level that you induce is certainly an adjuvant that will be more potent. This being said, and I think there won't be one adjuvant for all. You really will need to have one which will be specific to the immune response you want to induce in the population you're targeting. If you look at the data that AS01 generate, I mean, you could think this is adjuvant you use for everything. It is nonetheless a little bit reactogenic, and that's not something I think you can use for any type of vaccines, and there's no reason to use it for any vaccine. So.
Well, you're saying the AS01 in Shingrix is stimulating a CD4 T cell response.
Yes.
Yeah, right.
Yeah.
Are there other questions. Yes.
What do you think is going on in Shingrix?
I wish I knew.
CD4 response, but is it a better, is the antigen a better booster
I think we,
opposed to a monoclonal vaccine, or what do we have?
well, it's counterintuitive. Huh? So it's counterintuitive to think that the live vector is not as is worse actually than. Yeah, I think there are studies that are being done, but I don't think we have the answer yet, frankly. What is? Yes. In the Stavax. Still, you have the whole package.
It also has a high concentration of the important glycoprotein, so that helps. If not, no other questions, thank you very much.